The first step of the project was to perform a link budget analysis to ensure that the radio would operate correctly when in orbit. To do this, I performed manual calculations and then used MATLAB to confirm and validate the calculations. For MATLAB to be able to perform the simulation, it needs to know some basic parameters about the simulation, such as the time, the orbit, the satellite and ground station radio specifications, as well as the ground station position. With these parameters set up, MATLAB can produce a 3D image showing the satellite as it passes over the ground station, with the green line representing when communication is able to be established between the two. This takes into consideration more than just line of sight, also the signal strength. We can then use the link table function to determine the start and end time of each contact between the CubeSat and the ground station, and analytically determine the link performance. A plot of link margin can also be produced, and this, in combined with the start and end times of each contact, can give a really good indication of the amount of data that could be downlinked in one pass. The next step of the project was to simulate the transmitter system in Simulink. So you can see we're taking either pre-prepared frame data or a random data source and putting that into the transmitter system. Inside the transmitter, we take those bits and group them into bit pairs, which get mapped to a QPSK constellation and then pulse shaped. The transmitter system produces perfect QPSK symbols, as can be seen in this constellation diagram. After simulating the transmitter, I then needed to simulate the channel and receiver to verify the radio's performance. The channel simulation adds noise and a phase and frequency offset. The receiver must correct for these perturbations, which you can see shown progressing in these plots. The left plot shows the signal directly after channel filtering. The middle shows after fine frequency synchronization, and the final plot shows the signal after symbol synchronization, and you can clearly see the QPSK constellation. The next part of the script will take those symbols and demodulate the QPSK constellation to give us output bits. The script will also tell us what the error rate was for that particular part of the symbol, which in this case was 109 bits out of about 10,000, so the bit error rate is approximately 1%. With a lower signal to noise ratio of 4 dB, you can see this increases to 1.68%. Before we connect and power up the board, we need to make sure the boot mode switches are in the correct positions. I'm going to be booting from the SD card, so I need to have switch 3 and switch 4 in the up position. To set up the development board, the first thing I do is attach my anti-static wrist strap, then ground the board with another strap, then connect the power cable and the HDMI for the TV, as well as the SD card with the boot image. Then we'd connect the USB hub for the keyboard and mouse, Ethernet controller for streaming data to MATLAB, the transceiver board to the FMC connector, and the JTAG connector if we wanted to program the onboard flash. Then I hit the on switch and let the board power up. Lastly, I'll connect the SMA cable to the first transmit and first receive ports of the board. Now that the board is set up and turned on, I need to use a couple of setup functions in MATLAB to make sure it's configured in the correct mode, and then we can transmit some data by using the TX function. As soon as the data starts getting transmitted, the shape of the spectrum changes to a classic digital transmission spectrum. With the same data now being constantly transmitted from the radio, we can use the RX function in MATLAB to capture the samples from the transceiver. These samples then get run back through the same script that I used when simulating the radio. There's those three graphs again, with the data now looking a little bit different as it's real world data. The symbols can then be demodulated, and the resulting bits put through a frame decoding script that finds the frame headers and outputs the data contained in each frame. You can see this one says "Hello World." Thanks for watching. I hope you're able to learn about my project and radio development in general.